Hello and welcome to the 9th lecture of Machine Learning for Robotics and Computer Vision. In this lecture we want to talk about how to actually build successful convolutional network architectures and how to structure them. And before we start with this, we will talk about what happened in the last lecture. In the last lecture we talked about backpropagation, which was basically how to efficiently compute the updates on the weights in the convolutional network. We talked about methods, how to improve the actual convergence of the stochastic gradient descent in a way that we also can efficiently update the parameters in the end. But we also talked about how to initialize the weights so that we have a good starting point for the learning so that we can achieve converging networks in the end, but also talked about how to keep the learning active. And this was basically then using normalization layers in between, which ensured that the gradients are not exploding or vanishing in the end. And this was specifically the case with batch normalization. But in this lecture we will specifically talk about how to design successful convolutional neural networks. So learning is one part. The more important part is basically how do we spend the parameter budget in the end. So we have a specific number of parameters that we can maybe store on the GPU, and we want to spend these parameters in an efficient way. And the question is now, how do we combine these building blocks like the convolutions, the max pooling operations and the fully convolutional layers in a way that we efficiently use this to get a good performance for different tasks. And for this we are looking at successful approaches that were applied for ImageNet and the ImageNet competition, which basically is one good idea, because architectures that perform well in this task are usually also performing well in other tasks. So, and to just give a little recap, so we started with the so-called AlexNet, which was the winner in 2012, which had basically 8 learnable layers. The ReLU activation after each convolutional layer, and had something around 60 million parameters. And as I showed in the lecture, most of these parameters were basically stored in the fully convolutional layers. And this model combined an ensemble then with 5 different versions of this network trained with different initializations, then reached in the end something like 16.4% top 5 error on the test set of ImageNet. And I will now use in the following the structure that I show here: the convolutions in blue, the max pooling operations in purple, and then the fully convolutional layer, fully connected layer basically in orange. And as you can see, the network starts with a 11 by 11 kernel for the convolutions with stride of 4, produces 96 feature maps, which are then put through overlapping max pooling operations. Then we have 5 by 5 convolutions and so on and so on. So, and now the question is how we can get better results in the end using the structure. And this was basically then in 2013, the winning approach is basically a modification of the structure. So we have again 8 learnable layers and some refinements on a channel. And basically the one important part is maybe that in the beginning we had only a 7 by 7 convolution, which were much more efficient in the end. And this reached then already with an ensemble of 6 CNNs in the end, 11.7% top 5 error on the test set. But the question is now how we move on from this. So, and for this, one specific approach that was tried basically was to explore deeper networks, so with 16 or 19 learnable layers in the end. And this was the VGG Net. And one good thing about this network was that they tried to follow some design principles. So how to structure the network in a way that it's efficient and using the layers in a good way. And so, for this they decided to just use 3 by 3 convolutions all over the place, and then using max pooling operations which were non-overlapping. And one design principle that they followed here was that for the same feature map size, so after or before a max pooling operation basically, the layers have always the same number of filters. So the output number of channels is basically always the same inside such block. And then when a max pooling operation is happening, basically which reduces the size of the feature map by 2, because the max pooling operations are here with stride 2, they use the double number of filters in the end. So which ensures basically that the volume of the feature map is basically the same in the end. And for this, they proposed the VGG 16 and VGG 19 network in 2014, which had 16 and 19 learnable layers, and improved or increased the number of parameters drastically. So when you remember, AlexNet had something around 60 million parameters, and now we had networks that are basically having 138 million or 144 million parameters. And again, most of the parameters are basically, again, in the fully connected layers, but also the number of parameters in the convolutions were drastically improved. One specific case, as I said here, for the VGG 16 network, after a max pooling operations, the convolutional layers had always the same number of output channels in the end, or feature maps that they produce. And as you can see here, when we have a max pooling operations, this number is basically doubled. So we start with 64, then we have 128, 256, 512. So this is a little bit exception here, but in the end you had a max pooling operation and then do the fully connected layers again. So that's the same as with the ZFNet or the AlexNet in the end. One important part was here that to train such a deep network, some tricks were needed, because this was the time before using batch normalization in between. And this what made the training very hard of deep networks, because the gradients are maybe vanishing or in the end also maybe exploding in the end. So for this they are using a pre-training strategy, just using smaller networks and train it until convergence, and then using the weights that they got from this to initialize the weights of the larger networks. So they're copying basically the weights, and then they have only some layers left that are uninitialized in the end, and that they trained on top of this. And this reaches already a top 5 error of 7.3%. Unfortunately, in this year, also another approach was proposed, which even reduced the top 5 error again. So, and this was the so-called GoogleLeNet, which used also deeper networks. So this was basically the trend to increase the depth of the networks, and they used a specific architecture with multiple pathways. And why I'm mentioning here, because there was also some innovations that are also used later for the network. So this one innovation was basically using some inception layer, so-called inception layer, which has multiple pathways. Then the global average pooling, which replaces the fully connected layers in the end, or some of the fully connected layers in the end. And they introduced also this concept of the one-by-one convolution as a bottleneck to reduce the number of channels, to make the number of parameters not so large in the end. And for training, they had also to use some tricks, and this trick was here specifically to use intermediate losses to enable the training. Note, as I said, this was before batch norm, so therefore strategies like pre-training or this auxiliary losses are needed, and nowadays, because of batch norm, they are not needed anymore. The inception layer now looked a little bit different. So instead of committing basically to a specific convolution in one layer, they basically used all convolutions at the same time, so to say. So they had this 1-by-1 convolutions, the 3-by-3 convolutions, and the 5-by-5 convolutions, also a max pooling operation in the layer. And as I said, we have this multiple pathways, and to reduce the number of channels that got in, they had this 1-by-1 convolutions, which basically is just a linear combination of the input channels, and then reducing the number of channels from 192 to 16 or 96, and then using 3x3 or 5x5 convolutions. And then the output of all these convolutional layers are then concatenated again into a feature map size of 256. This was the inception layer. And one important part of this architecture was the so-called global average pooling, which basically enables to have then the output reduced to a vector that we can then use further. And the specific case here was that the average pooling now works on the complete feature map. So the size of the average pooling kernel basically is h times w. And this is applied to each feature map, and then this produces one number. And the global average pooling is applied in the end of the network, where anyway the feature map size are something like 7 by 7. So it basically produces the average of 49 numbers, and then you get out an output tensor of size Cn times 1 times 1, which is then put into a fully connected layer. And this removes basically the need, or what was before, that we had fully connected layer which reduced the feature map size to a specific number of output values in the end. And the structure now looked as follows. So we have here in the beginning again 7 by 7 convolutions, then a max pooling operation, then it does another convolutions on top of this, and it's so-called the stem of the network. And then we had the inception layers in between. And as I said, in the end, instead of the two fully connected layers, we have now this global average pooling, which produces then the 1024 output values, which are then used by the fully connected layer to finally produce the logits for the softmax that we want to have. In the end, we have 22 learnable layers, and to avoid the vanishing gradient problem, they had intermediate losses in between that ensured that the gradient could flow again. And when using this, they reached basically 6.7% top 5 error by using an ensemble of 7 models. So the question is now, so we are increasing now the size of the network. Can we go on with this infinitely? And so the question is now, can we maybe get by using deeper models always better networks or better performing networks in the end? And to this end, He et al. Made the experiment basically on, not ImageNet, but Cypher 10. And for this, they trained a network with 20 layers and compared this with the performance of a network of 56 layers. And when you look now at the test error over time, then you see that the 56 layer network basically reaches, saturates worse than the 20 layer network. So the question is now, with this larger depth, you get degrading performance. So what might be the reason for this? And one obvious reason would be maybe to say like, okay, with the Cypher 10 dataset, we are basically overfitting. So there's not enough data available. And but when we look at the training error, then we also see that the 56-dimensional 56-layer network is basically also getting a worse performance on the training set. So that means it's not basically overfitting. There must be another reason why this is happening. And the idea that He et al. Come now up with is like introducing somehow the ability that deeper networks, at least in theory, could learn the same as a smaller network in the end. And it comes down to something that we have a small network that is reaching a certain performance. We can basically embed this network in a larger network. And basically, when we increase the number of convolutions in the end, these convolutions maybe have to do something like an identity in between. So this would enable to have the similar performance as maybe a smaller network in a larger network embedded somehow. And the additional layers basically just have to be somehow identities to basically represent the same what we can do with the smaller network in the end. But how do we achieve this in the end, this identity mapping? And the clever way that they came up with were these so-called skip connections. So we have our convolutions in between, and then we are just adding basically the output from before. And by this, when this is basically 0, we are just bypassing the convolutions in the end. And this structure, the skip connections, really enable now the learning also of deeper networks in the end. And for this, they proposed the so-called ResNet, and for ResNet they had two basic blocks. The basic block, which were used for 18-layer networks and 34-layer networks, which basically was this from before, that we had the 3x3 convolutions and the skip connection, and for larger networks they introduced this bottleneck block, which basically used the 1x1 convolutions introduced by GoogleLeNet to reduce the number of parameters used. So when you think of it, these blocks come after each other, so we have 4 times C outputs, and these go in here, and then they are reduced by 4. Then we have our convolutions, and then they are upscaled again to 4 times the channel number. So you can see that really it's a bottleneck. So we are reducing the number of channels, and then we are expanding it again. And in between, we have, of course, now, because they were introduced in 2014, the batch normalization, which also enable to train these deep networks in the end. But important is that we have the skip connections in between, which enable basically to simulate a smaller network in a larger network, so to say. And for this, they introduced the so-called ResNets, which now look like this. So you have a reduced stem where we only have 7x7 convolutions. We have again the max pooling operations, and then we have this bottleneck layers with the specific numbers. Output channels 64, 128, 256, and 512. So the same idea as with the VGG Net. So after reduction of the feature map size, we are doubling the number of channels basically. And this is basically the idea taken from the VGG Net. And we have now not max pooling operations in between, but we have here operations that strided convolutions basically. The first convolutional layer after this dashed line is a convolution with stride 2, which basically reduces then the feature map size by 2. And this is now used as reduction in between. So in the end, we have again a 7x7 feature map size with 512 channels, and then the output of this is then 4 times 512, so we have 2048 values that we then put again in the fully connected layer to get our classification out. And the good thing about the skip connection is that we now can scale up the depth of the network. So in the end, they came up with a 152 layer network, which used basically the structure. So as you can see here, in red is the 152, so we have many more layers in between. There's 36 bottleneck layers there, and this reduced then the top 5 error again by a significant amount to 3.6 top 5 error in the end. And this was then an ensemble of 6 models. And when we now look at the progress on ImageNet, then we can see the common pattern, so that we started with 8 learnable layers, and then we are ending here with 152 layers. So after 2017, the basically the ImageNet challenge or competition was basically ended. So therefore, now approaches are not reporting anymore the test set error in the end, but the validation set errors, which are basically similar like the test set errors in the end, but then they have, of course, to use a different validation set in the end, which is the so-called mini validation set, which is extracted from the training data to fix the hyperparameters. But as you can see, over the years, there were significant progress by using these architectures. So with AlexNet, we started with 16.4% top 5 error, and with ResNet we reduced it to 3.6. In 2016 was an approach that reduced it to something like 3% by using an ensemble of different models. But from an architectural side, there was the improvement with the ResNext, which basically used the idea of GoogleLeNet, that you have the different pathways of convolutions in between and the squeeze and excitation pathway to further reduce the error rate in the end. So, and yeah, when we now think of this, we have more layers, we have also more parameters, and what now is maybe what is maybe a goal was now to reduce the number of parameters, to make it more efficient also to run on robots on mobile phones. So this is what we are interested in, basically having an efficient network which is also capable to run on embedded devices like the mobile phones or robots. And this should be efficient in a way that it can be fastly computed, so the computation time should be efficient, but also from the memory size. We don't want to spend so many parameters in the end, because this is a constraint that we have on robots and also on mobile phones in the end. So for this, the so-called MobileNet was introduced, which just replaced the convolutions that we have in the convolutional neural network by this so-called depth-wise separable convolutions. And the important part is here that by using this depth-wise separable convolutions, we can basically reduce the number of computations that are needed by a factor 8 to 9. And we can reduce this with only a small loss compared in the accuracy to normal convolutions. So how does the depth-wise separable convolution work? So we have again the feature map that comes from before, and we are not applying now the convolutions on all channels on the feature map, but have first convolutions that are working on just one of the feature channels. And this produces us then the same number of channels in between. And then we are using one-by-one convolutions to mix basically the feature channels that we get out from the convolutions. So we are basically now separated the channel-wise convolutions and the point-wise convolutions basically from each other. And by using this trick, basically, we can drastically reduce the number of parameters that we are using, and so also the number of computations that we are using in the end. And this mixing of the channels then gives us in the end then the number of the desired number of output channels. So here we have C-in number of kernels that we apply, and here we have C-out number of kernels that we apply on these feature maps by one convolutions to get then the desired output number of channels, like in the normal convolution. When we now compare this with the so-called MobileNet architecture, which is very similar to the ResNet architecture, and we just replace the convolutions with the depth-wise separable convolution, then we can see we have a small drop in the accuracy, but we at the same time have a benefit in the number of multiplication and additions that we are doing. So we are very efficient in computing it because we are using less of these operations. And we are drastically reducing also the number of parameters. So by using less parameters, we are basically getting a similar performance as just using convolutions. When we now compare it basically to the other architectures that we had before, the GoogleLeNet and the VGG 16, then we can see that we're getting a similar performance, but as before, by a drastically reduced number of parameters, which is also very important for embedded devices, is basically also a drastically reduced number of operations in the end. And what is also interesting is that we can also scale the network in a way, that we can reduce the number of channels that we are using, and by reducing the number of channels, we are also reducing the number of operations that we are applying, and conversely also the number of parameters. But we can see that by reducing the number of channels, we can see here a drop in accuracy, but this drop is not so drastic. So by only using half of the parameters, we can basically reach still 63% of top 1 accuracy here. And the same we can do for the resolution. So instead of using the 224 pixel images as input, we can use smaller versions of these images. Then the accuracy is dropping, but what is important is also the number of operations that we are using is reduced. The parameters stay the same because the convolutions are the same that we are applying in the end. And so the performance degrades gracefully with less parameters. And one further improvement on this, so with the after MobileNet, was introducing this so-called inverted bottlenecks. When you remember it from the ResNet architecture, we had this bottleneck which reduced basically the number of channels by 4 when we go in and then expanded this again. The inverted bottleneck is just doing the inverse of this. So we are now expanding the number of channels in this block and then reducing it to the number of channels that we want to have out in the end. So by doing this, we are basically, we don't have to do a lot of, we have here not the 4 times channels in that we then have to add in the skip connections, but we have a reduced number of operations there. And by using this inverted bottleneck, we are getting far more efficient from the memory perspective, but also computation-wise because we are using less operations in the end. And with this, we are then at the MobileNet version 2, which then had 20 learnable layers and had the bottlenecks. And the bottlenecks in this case used everywhere 3x3 depth-wise separable convolutions from the MobileNet architecture. As you can see here, we have in the beginning the 3x3 convolutions with stride 2, which reduces the feature map size. Then we had our inverted bottlenecks here with an expansion rate of 1. So we are basically not expanding the in the bottleneck the number of channels, but here we are then using the mbconf6, which is basically then an expansion of factor 6. So we are multiplying the number of channels that we have in the bottleneck by 6. And then in between we have again strided convolutions which reduce the size of the feature maps again. And the interesting part is now when we look at the results, when we compare this to the MobileNet, which were already very efficient in the number of parameters and the number of operations that we are applying. In the MobileNet, this number of operations is drastically reduced to 300 million instead of 575 million. And what was also good is that we achieve much better performance than the MobileNet, so 72% top 1 accuracy in the end. And this also leads then, because of the reduced number of operations, then also faster execution time on CPU from 113 milliseconds to 75 milliseconds. And what is now, what you can now do is by again increasing the number of channels. So by factor 1.4, we can increase the performance here, but of course then have the downside that we are also spending more parameters in the end. So MobileNet moved in the direction of using more efficient networks. So our parameter budget was more efficiently spent in the end. And what is also important for MobileNet is to use less compute operations, so floating point operations in the end. But until now, basically these structures are basically handcrafted. So one idea what people came up then is not just using these handcrafted architectures, but let the computer do this work. And this is the concept of the neural architecture search. So instead of using a handcrafted design, we can try to find automatically good architectures. And this is the so-called NAS, the neural architecture search. And in this neural architecture search, we have now 3 parts: the search space, the search strategy, and the performance estimation strategy. And the search space is basically the operations or building blocks and structure of the network that we want to explore. And from the structure side, can be then just using this linear stack of operations in between or layers, but it could also be having this parallel pathways that we have multiple parts like an inception structure, but also from the operations side, that we have different convolutions, the depth-wise separable convolution, for instance, but also maybe the activations that we are searching about. So this combination of all these parts of a network we can explore. And of course then the blocks that we have, maybe something like the ResNet blocks, the inception blocks, or maybe the inverted bottlenecks that we then combine. So this is basically the things that we can combine, and then the task of the search strategy is to come up with instances from this search space. So specific structures that we want to then evaluate or build. And for this, there are 2 prominent approaches. One approach is the so-called reinforcement learning, where we have a reward function, which is based on the performance of the network, and then leads to combining this in a more efficient way. And one other prominent approach is the so-called genetic algorithms, where we have a structure, and then by mutation and recombination, we can build new structures out of this. And this is basically producing new architectures in the end. And when we have this new architecture produced, which has basically as input the performance of the last architecture that we are explored, basically, we now have to decide how good or how well does the selected architecture perform. And of course, it's not the best idea to just train every of this network until convergence. So people came up with the ways of quickly getting an estimate of the performance. And one common way is to just use a shorter training cycle, not maybe train it with whatever 300 epochs, but maybe with 100 epochs, and then take this performance that we get out after 100 epochs as performance estimate. But we can also maybe try to extrapolate the performance only from a few examples that we are from which we are learning, and then extrapolate the performance for the whole network when we train a full on the full ImageNet, maybe, for something like this. Or we just can speed up the training by using the idea of the VGG Net, that we are just copying basically some parts of the weights from before into this new structure, and then we are already starting at a good point. When we apply this, then this is still very computationally expensive because we have to explore a lot of structures, but we can get out structures that are maybe not something that we maybe can get out from handcrafted design, which is maybe also a little bit difficult then to interpret. When we, for instance, have this MobileNet, which was basically generated by a neural architecture search, we have this linear structure, we have reduction cells and normal cells. So this is the normal cell that looks then like this. So we have some separable convolutions, but also some average pooling and max pooling in between. And this structure looks quite complicated in the end. But it leads then to solutions that are also performing better in the end on the ImageNet data set in the end. But the neural architecture search can also be used with specific targets in the end. So here's maybe the target accuracy in the end, but we could also use it with the right search space to also reduce the number of parameters in the end. So we want to maybe get a good performance with a specific number of parameters, or we want to achieve a specific number of floating point operations, so the flops, or we have a targeted architecture, so architecture in a way like we want to target it maybe as mobile phones or specific robotic platforms in the end. And therefore, neural architecture search is often used in these cases where we maybe decided on specific building blocks and then just to figure out how to combine these building blocks to achieve the specific objective. So when we now look at the results on ImageNet, then it becomes clear so that by increasing the number of parameters on the x-axis, we are getting better performance. So here's the top 1 accuracy. Here we have basically the ResNet 152, and here on the blue curve is basically different upscaled version of the MobileNet, and the MobileNet reaches now something like top 1 accuracy of 83%. And the question that now Tan et al. Asked themselves is basically, is this really the trade-off that we have to do, so always using more parameters to get better performance, or can we maybe get away with less parameters? And how we actually do the scaling, so is it just using more depth or more channels? And this is then the question that was investigated. And the important question is here how to efficiently scale a network. And for the model scaling, we already discussed this a little bit with the MobileNet. There are different ways. So here we have some network architecture. We can introduce more channels. So this is the so-called width scaling. We can increase the depth. So this is also maybe some pattern that was used then in the ResNet, where we added more blocks in each stage in between, and to make it deeper, the network. But we can also increase the resolution of the input image and then maybe get better performance. But when we now look at the individual parts, so here the number of channels, the depth of the network, and the resolution that we are using as input, then you can see that the performance for each individual part is basically leveling off at a certain percentage of top 1 accuracy here, something around 80%. So individually scaling the depth and the width of the network, but also the resolution, gives us diminishing scaling properties in the end. So there's some limit where we not reach much better performance by scaling it even further. And the question that Tan et al. Now ask themselves is basically, can we maybe do better? And they come up with the interesting idea of compound scaling, which means that we are scaling now not only one parameter like the depth, but together with the width. And using this idea, here on the left is a plot shown where we have the base structure with some specific depth and resolution, and we are scaling this just linear up. And when we are using different factors for the depth and the resolution, then we can see that we can reach much higher accuracy in the end. And then here on the right is the plot shown for the individual ways of scaling it, like in yellow scaling it by the width, with blue the scaling by the depth, and with green the scaling by the resolution. Then we can see that it levels off something around 80%. But when we combine this, so when we are having specific factors to scale that at the same time, then we can see that we are reaching much better performance in the end. And what Tan et al. Now did is to look at a specific baseline model, which basically can then scaled up to get better models in the end. By this, introducing a whole family of models that are in a way efficient in the end. And for this purpose, they applied the neural architecture search again. And here the goal was to apply, to search a structure that is not only accurate, but also computational efficient. So it goes in line of this MobileNet architecture. So also the architecture looks very similar to the MobileNet version 2. We have again the inverted bottleneck structures here with expansion rate 1, 6 in between. And now the number of channels changed because the neural architecture search came up with this number of channels. And what additionally is done is that the inverted bottlenecks not only use 3x3 convolutions in between, but also 5x5 convolutions. So in brackets here are the number of the dimension of the kernels that are used for the convolutions. And So again, using depth-wise separable convolutions in between, and by using this, they get very efficient networks out of this. So when we compare this to the MobileNet version 2, which had 3.4 million parameters, then we're getting a top 1 accuracy of 72%. And when we are now using this base model of the EfficientNet, which is called B0, we are getting already 77.1 top 1 accuracy, but with a much reduced number of parameters, 4.3 million. Compared this to the MobileNet, to the ResNet, which had then 26 million parameters, and reached a top 1 accuracy of 76%. And when we see this now on this curve, then we can see by scaling then up this network with the compound scaling, that we are scaling the depth, width, and resolution at the same time, we can get very efficient networks that reach even top performance on the ImageNet dataset. So this is one direction which one can go with this, so that we want to reach more efficient networks, so using less parameters in the end, and by scaling this up in this compound way, we are getting a family of architectures that can be used efficiently to get very good performance. So when we now look at the current trends that are investigated in the convolutional networks, then we have the so-called normalization-free networks. So, and here the interesting idea is that we can get away with not using normalization layers in between, so something like batch normalization, but by using a specific weighted adaptive gradient update to avoid the problems that we usually have when we are not using some normalization layers in between. And the important part here was that by not using the batch normalization in between, we get more efficient training, so we can train faster the network basically. But of course, the downside was, or compared to EfficientNet, that the models get very large in the end. One interesting idea is then to not only look at how we get more efficient networks, but what we can maybe do by using some existing structures like ResNet, by using the scaling strategies, but also by improved training. So, and Bello et al. Showed in their ResNet RS structure that you can basically, by just using small architectural changes, but using more efficient training adaptations in the strategy of the training, that you can get even very good results with just the normal ResNet structures. And because the ResNets are also then faster to train than the EfficientNets in the end. So, and this was maybe also the motivation then for Tan et al. To look again in the EfficientNets, and then the EfficientNet version 2 improved on the training efficiency in the way that they are replacing in the inverted bottlenecks the depth-wise separable convolutions in the earlier layers by just normal convolutions. And by using this, they found out that basically the training efficiency is much improved. So the EfficientNet version 2 is much more efficient to train, but reaches similar performance with slightly increased number of parameters in the end. But when you now look at this, then you would maybe ask yourself, okay, you have now these different architectural choices, which is basically the architecture which I should maybe choose for my task. And one recommendation that one can make is basically to start with something which is already there. So don't try to come up with a novel architecture, but start with something that you already know that is performing very well. And for this, the basic model over the years was basically ResNet 50 or something like this, also some kind of ResNet, which is providing a good baseline for the training and for the structure. And it showed very good performance. So And nowadays maybe EfficientNets are a good starting point when you want to have specifically small models in the end. And the current research then also maybe focuses more on more efficient training in the end. So you always have to look out what's happening in the research, because it's a vibrant research field with producing every day maybe new insights about how to train and how to structure it. And what can also be shown is that by using these improved training strategies, that you get also promising improvements even for the old ResNets in the end. But when we talk about training of the networks, we have also to talk about the overfitting or the generalization ability of the network. So usually what we mean with overfitting is that when you train and your training error is decreasing, and at some point the validation set error is increasing again. So, so one common strategy is to basically stop then at a specific point, so that you have this early stopping strategy that we also talked about in the tutorial. But what you also want to have is basically the gap between the training error and the validation set error should be as small as possible. So you want to have on unseen data, a model that also performs very well. And so even if you not have overfitting, so the question is now, how do we ensure that the model that performs well on the training data is also performing well of unseen data? And the common strategies for this is basically some adaptations of the network in a way that it modifies the way in which we update the parameters in the end. And as I said, one easy solution to avoid overfitting is in the end just looking at the validation set error, and if it increases again, just stop there. Other strategies are L2 regularization, dropout, and stochastic def, which I will cover next. But what we also can do is basically a data-based adaptation. So by modifying the inputs, we can get maybe better in the end. So we talked already a little bit about data augmentation. We will now talk about RandAugment, mixup, cutout, and cutmix. The general idea is basically to make it harder to overfit for the network by adapting the input data, but also by doing some changes on the way how we update the parameters so that we are not overfitting in the end. And usually it's both a combination of the network-based but also of the data-based adaptations. So one common thing that we also applied for the softmax regression was to use the L2 regularization, which is basically reducing the risk of overfitting by keeping the parameters small in the end. So we add in the loss a term that increases with the size of the parameters in the end, and this is usually then applied in the gradient update, so that we have this so-called weight decay. And the important part is here that we apply this weight decay basically only on the weights of the convolution and fully connected layers, but not on the biases and the batch norm parameters in the end. They are staying unregularized. And one has to keep attention here. So the L2 regularization and the weight decay is basically the same when you're using something like stochastic gradient descent, but it turns out for ADAM, for instance, that is not the same. So there you can look up in this paper specifically how you adapt basically ADAM, or you can just use the ADAM-W approach, which provides this adaptation in a way that it is then working well in the end. So we have regularization. We can also do regularization in a different way. So this is also something that I mentioned when we talked about AlexNet. And this is a common approach applied for the fully connected layers to have dropout. Dropout is basically just blocking some part of the parameter update in the end. So we are not adapting all parameters at the same time. And by using this, we are avoiding the co-adaptation, so-called co-adaptation of the weights. And when you think of it, by dropping out randomly for specific kinds, you basically have something like a built-in ensemble in one model because it takes always different parts, and by dropping out with a specific probability, the neurons are less likely to adapt in the same way always. And as I said, this is usually applied in the fully connected layers, and at test time we had then to scale these activations to account that only part of the network is learning basically for specific examples. And this scaling is then something that you have to do in the end at test time. One interesting idea is not to do only the dropout for the fully connected layer, but also in between somehow. So, and here we are dropping out basically complete layers in the end. When you have this ResNet structure, you have the residual blocks, or this blocks with the convolutions in between, and you have this identity. And what you can now do is, in this approach with the stochastic depth, that you deeper you go in the network, the more likely it gets that the convolutions are just turned off in the end. So we just have the skip connections. And similar to the dropout, we have an implicit ensemble with this, and we need then to scale the function accordingly to the probabilities in the end. But it has been shown that by using this idea of stochastic depth, you basically can learn much better models in the end. So these are the updates that we can do, or the ways that are usually done to adapt the parameters in a way that we can avoid overfitting or get good results on unseen data. And one other common way to do the database adaptation, or the database prevention of overfitting, is basically the data augmentation. So as already done with the AlexNet in 2012, basically is to provide the network just with more examples, where it basically should not make much a difference in the outcome, and to make the network learn basically some invariance in the end. So the data augmentation is basically an effective way to increase the training set size by providing new images, by maybe doing horizontal mirroring, or doing a crop and resize operation, or maybe just changing the colors by making the saturation a little bit different. And so the augmentation basically provides additional cases that the neural network has to deal with. And so, as I said, common augmentations are the mirroring, the color distortion, but also shearing and cropping. And to push this a little bit further, the so-called RandAugment was proposed, which is then a combination of different augmentations in a way. And the important part is here that the augmentations are not always done in the same way, so they are combined differently, so to produce new examples, and they are also done with the magnitude from very slight changing of the image to larger changes in the end. And these parameters of how many augmentations you use and how much you change the images in the end is basically a hyperparameter that you have to determine for the specific data. In the interesting cases now, when you're doing this RandAugment, then you get improved performance on the test set in the end, but you can also apply it to different other tasks like object detection. And the performance may be better to other automatic data augmentation methods, but the advantage is that it doesn't need some additional training on top of this. And as you can see here, the search space over different augmentations is basically drastically reduced in the end, because it's just these two parameters that you have to find to get a good result in the end. Not only using maybe the specific adaptations of the images by modifying the input image, another idea is to so-called mix-up, where we just build linear combination of different examples, something like here this dog and this cat, and we are just mixing this together into one image, and then we are providing not a label which is just 1 or 0 for the specific cat or dog class, but it's just a linear average between the different classes. So when we are using basically 1/6 of the cat image and 1/4 of the dog image, we are also then modifying the label in the end. And the assumption is here that the linear combination of inputs should also lead to linear interpolation of the asserted targets in the end. And by using this, one can think of that we are producing examples in between on the decision boundary between these two classes, and want the network also to perform well for these examples. Another idea is to just remove some part of the image. And by using this cutout, we randomly cut parts of the input image and replace it maybe with the mean. And by using this, then we are getting this augmented image, which we then can also use for training. And to push this a little bit further, so something in between, cut out and mix up is in between the cut mix, where we are just using crops of the input images, then put them together and then provide again this mixed label in between. And this is similar to the mix-up. And when we now look at this different data augmentation strategies or data-dependent augmentation strategies, then we can see here the usual ResNet architectures for different tasks like classification, localization, and the detection task. And then by using the mix-up and the cutout, we get improved performance here for the test set, but or for the validation set. And when we are using cutmix, then the performance is more improved in the end. And what was interesting about this cutmix idea is that we also get good performance basically also on different tasks like detection, object detection. So really ways to using the strategies. So these are the improved training strategies that I talked about for using the ResNets. And by using the strategies, we can usually increase the performance of our approach in the end. But it's not only using this one strategy, but it's usually using the combination of multiple strategies. So for instance, for the EfficientNet, they use this auto-augment, which is similar to RandAugment, but it's specifically optimized for ImageNet, basically to use this specific augmentations in a specific way. But it's very similar to RandAugment. The stochastic depth, of course, and dropout was applied for EfficientNet. So it's really a combination of different ways to reduce the risk of overfitting, and also to reduce the gap between the training and the test error in the end. For EfficientNet 2, there was used the RandAugment, and on top of this then the mix-up, for instance. And for the normalization-free networks, this was basically a mixture of half of the batch was used with mix-up, and the other half of the batch used cut mix in the end. And then on top of this random augmentation with even 4 different augmentations that were used for the randomly augmented examples. But as I said, similar to the hyperparameters, these are usually highly data dependent. So there's again no free lunch, so it's something that one might want to try out. So, but these common strategies of using dropout or maybe stochastic depth or something like this showed very promising results over a wide set of different tasks. So, and with this I'm coming to an end. So in this lecture we talk basically about popular and significant architectures, and as I said, so basically you take one of these later architectures, maybe something like ResNet as your starting point, and from this you can then maybe adapt it to the specific task. And we saw the evolution from using many fully connected layers then to maybe using just the global average pooling, then using skip connections, which is basically the thing that all architectures after that used in some way. So also the MobileNet and EfficientNet are using this skip connections, and then going in the direction of using more efficient networks. And as I said, we started with VGG, GoogleLeNet, then ResNet, came to MobileNet version 2, which improved much on the efficiency on using less parameters, but also compute operations in the end, and then the EfficientNet. And we looked at common ways to reduce the gap between the training and test performance, to reduce the generalization gap in the end. And for this, I introduced some different strategies that you can use there. And thank you for your attention, and then see you next week.